Welcome back to Elements of Chemistry tutorials. In Chapter 7, we're going to talk about the periodic table, perhaps our most useful tool in our arsenal of chemistry skills. Okay, the periodic table is always credited with Dmitry Mendeleev. In 1869, he was a Russian chemist who did all sorts of things. He was kind of a Renaissance man in Russia. But he's most credited with development of the periodic table. But like all discoveries, his work was built on the shoulder of giants, others that came before him. In 1829, I'm going to say the name wrong, I'm sure, Johann Dobrinner first grouped elements into triads based on weights and properties. He had a triad, called it Group 1, with lithium, sodium, and potassium. They were elements that had similar properties. They reacted alike. If you added them to water, they reacted violently. He had another triad with chlorine, bromine, and iodine. They also reacted in a similar way, as did calcium, strontium, and barium. So he grouped elements into these triads on weight and properties. Remember, this is well before we knew about the atom. Then a little later, in 1864, John Newlands built a table based on what he called the law of octaves. He found a repeat in properties every 8 elements. Still, we did not know about atomic number. We did not know about protons. He just found that based on mass, or weight of the atom, the element, there was a repeat. Later on, that same year in 1864, Lothar Meyer built a table based on atomic weights, not on properties. And here he had a tabular form, and we still sort of see this law of octaves being reflected here. So Dmitry Mendeleev worked on these things. He built this into his groups of elements based on weights and properties with a repeat occurring every 8 elements, the octave. The brilliance of Mendeleev's table was in his acceptance that he did not know everything, and that all elements at the time his table was designed, we didn't know everything. So he left important gaps, and he was able to predict weights and properties of undiscovered elements with great property and great accuracy. He could say, well, the boiling point is going to be such and such. The mass will be such and such. He even argued with discoverers and found errors. He was able to predict in 1875 the discovery of gallium, in 1886 germanium, also in 1886 scandium, and 1898 polonium. The key point here is that in 1869, the concept of the atom was not generally accepted. We didn't know about subatomic particles. We didn't know what was going into these things. So here's another view of Mendeleev's table. They put it in lists. They weren't really put in that tabular form that we're used to seeing, that table, until much later. Following up on Mendeleev's work, and it wasn't accepted by everybody at the time, we had Lord Rayleigh and William Ramsay. They discovered the noble gases and found that they fit perfectly in Mendeleev's table, and they placed them in group 0. So they actually went what we would call the front of the table. So you can see that helium is by lithium and neon is next to sodium. There are some tables that are circular and they connect. It wasn't until later that we actually get the table that we have. Our next big achievement came in 1913. Henry Moseley. He was trained at Trinity College in Oxford and appointed a physics lecturer at the Rutherford Labs at University of Manchester. From our discussion of atomic history, we know how important the University of Manchester was, and Rutherford. So here he's at Manchester, he's working with X-ray scattering. He altered Mendeleev's table, changing the order to be atomic number. Remember, that's the number of protons. Instead of weight, protons plus neutrons. This corrected the problem with argon and potassium being in the wrong groups, as well as tellurium and iodine being in the wrong groups based by properties. When he fixed it by mass, we got everything pretty much into the right place. The key here is Moseley's law, which connected the lines in the X-ray spectrum to the number of protons in the nucleus, so he effectively discovered what we now call atomic number. This was really early on in his career. World War I broke out. Being a very patriotic young Brit, he joined the military, he enlisted, he was sent to Tripoli in Turkey, and he died by sniper fire at the Battle of Suvla Bay. He was only 27 years old. and the world lost a brilliant experimental physicist. His death in combat led to a change in the military draft policy for Great Britain, where scientists would henceforth be protected from combat duty. We needed to protect those great minds, which led to the US intellectual exemption from the draft. If you were a student, you couldn't be drafted. Shortly after Moseley, Niels Bohr, remember Niels Bohr was the one who put electrons into orbit. He was working with light spectra, same thing as Moseley. He worked with the atomic number and devised a table that looks something like this. Remember, we're still seeing lists of elements. So this is Bohr's modification, and he still left gaps, saying that things would be soon discovered. Okay, if you notice in our timeline here, we have 1920s, 1930s, loss of economy, fall of the stock market, lots of things just kind of stopped. In the early 1940s, Glenn Seaborg came in. He moved the rare earth and transuranic elements into the lanthanide and actinide series. He is credited with the horizontal form of the table that we often use today. Here's what the table kind of looked pre-1940. And then shortly after, in 1944, you see we've got lanthanides and starting on the actinides. Now notice the table is pretty incomplete. By here, we've got a lot more elements than we had in Mendelev's time, and we started to put them into order. Now, the neat thing about Glenn Seaborg is he put them on these lanthanide and actinides. These elements have properties more similar to themselves than the other transition metals. So when we think of lanthanum and actinium, which fit there at that D1 spot, if you remember from electron configuration, all of those other elements in that series stack on top. So literally the F block elements are sitting on top of the D1 lanthanide, D1 actinide, and they build up to get their 14. In 1941, Seaborg discovered plutonium at Cal Berkeley. That discovery was not announced until after the war in 1948. While during the war, he was working on the Manhattan Project, americium, and curium were discovered while he was working at University of Chicago. Legend has it that Einsteinium and fermium were discovered from the fallout of hydrogen bomb testing. And then later, mendelevium, nobelium, and finally seaborgium were discovered at Cal Berkeley. Seaborgium is obviously named for Glenn Seaborg. He is the only living scientist to have an element named after him while he was still alive. So what's next based on quantum theory? Well, the periodic table will continue. We have already completed our 7th row. That Francium row is complete, and then we will go on and add an 8th row. Our lanthanides and actinides are complete. The next F block elements are going to be called superactinides. In my research, I found a really cool site. It's 300 years of the element discovery in 99 seconds. I really hope you take some time and just watch this. It's 99 seconds, and it's really cool to see how the elements fill in the table. They are filling in the modern form of the periodic table. Now that we have 118 known elements, 119 should be coming soon. I hope this gave you a little bit of overview as to the history. I left a lot of people out, but gave you some of the main players there. As always, stay curious, be safe, have a wonderful day and a great tomorrow. I'll see you back on Elements of Chemistry.